Now that we know why it's important to study stars, because that's where we come from, let's take a look at some of the different types of stars that are out there. When we are looking at stars, there are certain things that it is important to know about them, certain characteristics that astronomers want to know. Size, both the mass and the actual radius size. Color, temperature, two things that are closely related. Spectral lines, which we looked at with spectrum analysis. How long is that star going to last? And then how is it going to die? All things that we're going to be looking at over the next couple weeks. Take a look at this photograph and then see if you can answer in your head which stars are the hottest and coldest. Which ones are the biggest or the smallest in diameter? Which ones are the brightest or the least bright? In order to answer these, hottest and coldest, you look at the color. The biggest or smallest in diameter? Well, wouldn't you also need to know how far away that star is? The brightest or the least bright? Again, isn't distance going to be pretty important to figure out which ones are truly the brightest, which ones are truly the dimmest? So just by looking at this photograph, you don't have all of the information that you need in order to answer all of these questions. We're going to figure out how to answer these though over the next couple weeks. Obviously, temperature and color, that was Wien's law. We've already looked at that, so I'm not going to spend a whole bunch of time on it. I just want to remind you of it. But I do want you to sketch a visual representation in your science journal of this following idea. Hotter the object, blue. Colder the object, red. We're going to come back to that idea quite a bit when we're looking at stars. Hotter the object, blue. Colder the object, red. And then I want you guys in your science journal to create this chart using an entire page. Fill up an entire page in your science journal, and over the next couple weeks we're going to fill in these columns. It might look something like this. And the first column that you're going to fill in is the temperature. So go ahead and fill these in. And class O is the hottest. What color do you think that is going to be? Obviously blue. Class M are the coolest. What's that going to be? Red. Here's the rest of the colors. Go ahead and fill those in. Our sun is about 5,800 degrees. Our sun is a class G star, which is classified as yellow. And you might remember me telling you that our sun is white when we look at it. Why would astronomers classify it as yellow? Well, it has to do with what's known as a color index. Long story short, you take the peak wavelength of two different types of light and you subtract them, and when you do that, you get all of this. If you want more information, there is the equation that you need to use. Bottom line, the sun looks white to our eyes, but it's classified as a yellow star. Might seem to be contradicting itself, but we're just going to go with it. It looks white. It truly does look white when we look at the sun. Don't do that, by the way. But it's classified as a yellow star. That's just what we're going to go with. Let's take a look at some of the sizes of stars. I love videos like that. So let's take a look at some of the different sizes of stars that exist up there. First, I want to see if you guys can find the sun. If you look closely, is the sun up there? In fact, the sun is right here in the very middle. And it's actually invisible to you guys. It's less than 1 pixel big. In order to have a star like Betelgeuse fit on the screen, to scale, the sun is too small to even show up. And our sun is huge. As a reminder of just how big the sun is, here's Earth. You can fit over 1 million Earths inside the sun. It makes up over 99% of all of the matter in our solar system. It is huge. There's really nothing else to say about that. So there are some stars out there that are absolutely ginormous. Here's our sun, and this is Antares. Not even the biggest star, but this is Antares. And if you put Antares where our sun is in our solar system, well, the orbit of Mars would be right here. So this star would actually extend out past where Mars orbits. So we would actually be in here towards the center of the star. Betelgeuse, which we talked about yesterday, it's going to go supernova sometime soon. It's in the shoulder of Orion the Hunter. If you put Betelgeuse where our sun is located, it goes out between the orbits of Mars and Jupiter. Here is the orbit of Earth. So Earth would be orbiting roughly just outside of the core of this star. Needless to say, this is a big star. And this is Betelgeuse next to VY Canis Majoris, which for quite a while was the biggest star that we had ever found. Next to our sun, you can barely see the sun next to this star. Earth's orbit in comparison, I don't really have the right adjectives to describe how big this star is. Here is VY Canis Majoris. Here's NML Cygni in Cygnus the Swan, and then UY Scuti. This is right now, currently, the biggest star that we know of in the known universe. Will it stay that way? Well, once James Webb gets up, we're going to find a bunch of new stars. So this will probably not be the biggest star for much longer, but right now, currently, UY Scuti is the biggest star that we know of. And if we were to put UY Scuti in our solar system, Earth's orbit would be right here. Earth would be in the core of this star, Jupiter would be inside of this star, and Saturn would be right next to the star. Let's just be glad that this star is not replacing our sun, because we would literally be in the core of this star. That's how big it is. A couple more things to fill in your chart. The average radius in sun radii for these stars, as well as the average masses in solar masses for these stars. Again, our sun is a class G star, so 1 solar radius and 1 solar mass should be down here for class G. Now I want you guys to take a look at the data that you've written down so far. And I want you guys to try to identify 2 trends that you see already as you go from an O-class star down to an M-class star. What are 2 different trends that you see in that data? Do a quick review.
What do you see when you look at the night sky? Depending on where you live, you see mostly stars. If you look at the sky without a telescope, you see white stars, maybe some faintly blue, or even sometimes some yellow or orange ones. The color depends on the star's surface temperature. For example, our sun's surface temperature is about 6,000 Kelvin. Although it looks yellow from Earth, the light of the sun would actually look very white if we were in space. This white light coming off the sun is because its temperature is 6,000 Kelvin. If the sun were cooler, it would give off light more in the red range, and if the sun were hotter, it would look more blue. The coolest stars in the universe are the red dwarf stars. These are very tiny stars, some of the tiniest, so they don't burn as hot, and their surface temperature is only 3,500 Kelvin. The light they give off looks mostly red to us. Red is also the color you see with red giant stars, huge stars that ran out of hydrogen fuel and bloated up many times their original size. The luminosity of the star is spread out over the much larger surface area of the red giant, making this star cooler than other large stars. On the opposite end of the color spectrum are the blue stars. These stars are giants and hypergiants, much, much bigger than the sun, and also much, much hotter, between 10,000 and 40,000 Kelvin. For us on Earth, though, most stars in the sky, except for the brightest ones, appear white or bluish-white because they don't emit enough light for our eyes to see color. Scientists have been studying stars for a long time, and over time they have learned to tell a lot about a star just by determining its temperature and atmospheric pressure. The temperature tells them the surface brightness of a star, and the pressure tells them an approximate size of the star, which tells them whether the star is a giant, a dwarf, or something in between. These two measurements, taken together, can often give information on the star's age and distance from the Earth. Scientists like to organize and classify things. They developed a classification system called the spectral code and have used it since 1943. To those who can read it, the spectral code tells just what kind of an object a star really is, its color, size, and luminosity compared to other stars, in addition to its peculiarities, history, and future. Let's learn a bit of the classification system. Scientists classify stars by temperature and the elements they absorb, which are called their spectra. They have divided stars into 7 main types. There are 7 main types of stars: O, B, A, F, G, K, and M. The O stars are the bright, hot blue stars, and the M stars are the dimmer, cooler red stars. According to the modern spectral classification system, O stars are blue, B stars are blue-white, A stars are white, F stars are yellow-white, G stars are yellow, K stars are orange, M stars are red.
Biggest